Okay, guys, let's get started. This is what, the sixth review session? Sixth review session. Okay, good. First problem. So is this alkene cis, trans, or neither? This we could just do together so I can save an apple for the harder problems later. Neither, right? Because why? Because if you flipped it, okay? If you flipped it, so neither is the correct answer. If you flipped it, we look exactly the same because of symmetry. Okay, so this would be the flipped one, and they're the same because you could just, you see, you can just take the compound on the right and turn it over, like rotate it like this by 180 degrees, and it will be the same. Okay? Yes?
What if one of the oxygens was a carbon?
What if one of, that's a very good question. So what if we had this compound instead, right? With one of the oxygens being a carbon, for example, CH2 over here, or we would just draw it in a line drawing, it'd just be like this. What about then? Then it would be so then there is another nomenclature which I'm gonna show you. This is called E or Z. E means on the same side, Z is on the opposite side. Then what you do is you basically do something. It's kind of like cis and trans, just a little bit more formal. So you would be, then the oxygen with higher atomic number takes precedence. So this is priority A. This would be priority B. Here this would be, hydrogen is priority B. And this is priority A, the carbon. So then you see they are on the same side with the higher priority. So there would be Z for zusammen. So it would be Z versus and not E. But it's kind of like E is like kind of like cis.
Because the top
Yeah,
priority is
because you would do it by the priorities because oxygen has higher priority than carbon. But yeah, in this case it would absolutely matter. Yeah. It does not matter in the case of this one. That's neither because it's the same. Okay?
Thank you.
Yeah, you're welcome. Good question. So I'm going to take off this stuff. Let's see. Okay, let's go to the next problem, right? Because they're going to get harder. So this one. Do we have this twice on the problem set?
No, you just have the same molecule. We've asked a different question on that one.
Oh, but I'm asking for something different.
Yeah.
Okay, because I realized I saw the molecule twice. I was like, why? Okay, so this is Crestor, right? That's a medication used to reduce the cholesterol level in the blood. And the question is it cis, trans, or neither? This guy. Let's do this one together as well. So this double bond here, indicated with the arrow, right? What do you guys think? This is trans, right? Because the big groups, they are on opposite sides. Okay, so here's the plane of the double bond, right? Like this. This would be the plane of the double bond. Or just going through like this, coming out the board, okay? And so they are on opposite sides. See, one of the big groups, this one, is pointing to the right. And the other big group, this whole thing here, is pointing to the left. So this is trans, okay? So so trans is the correct answer, okay? So now let's move on. I think they're getting... So the cis-trans stuff is really not too difficult, I think. It's easier, in my opinion, than doing the RRS thing or Fisher projections and stuff like that. Okay, but I still recommend you do some practice problems about it so that you're rock solid on getting the cis-trans problems right. There will be a few of them on the exam. Okay, so now this next one, I'm not really asking for R and S yet, right? Because I can't ask for it because I'm not drawing the dashes and wedges. But it's a similar, there will be, you guys saw the practice exam. I think there is a problem, as far as I vaguely remember, there was a problem like this on the exam. So I'm going to give you a big molecule, draw it without dashes and wedges, or maybe with some, right? I'm just going to ask, locate the chirality centers. So you either have to circle them, or the best thing to do is just, you draw the asterisks wherever there is a chirality center, okay? So who wants to try? Just try to draw them in. You can try? You had a question? No, okay. I just saw you raise your hand. Somebody wants to try? It's very good practice. You want to try?
Not gonna go well.
Huh?
Is this an apple?
Say again?
Is this an apple?
This is an apple. Yeah,
Yes.
now the apple
Okay.
start.
Cool.
Whenever you have to draw something.
Here.
I think I have enough apples. This is a big apple.
Sweet.
It's a lot of chirality centers. I don't know.
Oh,
So just put
no.
an asterisk wherever you think there is a chirality center.
That's what I thought. Okay.
That's correct. That's one. How do we find out whether there's whether there's a chirality center or not on for example on a carbon atom? If you have 4 different substituents, right? So that's absolutely one. Okay.
Okay. And then can I think out loud about the next few?
Yeah. Feel free.
Okay. So just directly to the right, I don't think that that's one because there's like a
Can you circle the carbon you're talking about?
this one.
This one, and
I don't
that's
think-
not. Why is
no.
it not? So we will undo here, right?
Oh, sweet.
So why is it not a chirality center for people?
Because of that double bond, 2 of those are the same. Like it's the same substituent. Is that right or no?
No, because how many substituent does that carbon have?
It only has 3.
It
so
only
it
has
to
3
have 4.
substituents, right? And what we said in lecture is and the other thing is the geometry, right? So if you have 3 substituents, right, because of the Vesper model, because it's sp2 hybridized, it's all flat, okay? And now remember, a chirality center means that you make the mirror image, and the mirror image is not superimposable, right, on that carbon. And so if it's flat, any flat structure, right, will have a mirror plane going through it. So any flat structure, any flat atom cannot be a chirality center, because if you mirror it, you can just rotate it over and superimpose it.
And how is that flat?
Oh, just
Sorry,
the
what
carbon.
part?
So here, this part, right?
Okay.
This is flat.
Okay.
This is it's trigonal plane of geometry.
Oh, I
right?
see.
Right? Because
Yeah.
it's sp2 hybridized.
Okay.
And then that's why it's flat. It's all in one plane. I mean, it's just that carbon. The rest of the molecule is not flat. Okay?
Okay.
So that's why it's not a chirality center. So chirality center needs 4 substituents. 3 substituents is not enough. Okay?
Okay.
So let's
Thank
see.
you.
There's more in there.
Yeah, see, and I
I just give you the apple as a prepayment. You don't really keep going.
I
So far, you're
see,
doing a good job. Okay.
and I don't see more. So just going around that first ring, there isn't
Yeah.
one on the bottom. There's not one there. Or
Keep going around the first ring.
Okay,
So what
so-
about the next carbon?
so carbon 3.
Yeah. Can you circle it so we know which one we're talking about? Okay. And then you can just always keep on doing
Yeah.
it, right? So,
So-
that one, it's also
No.
sp. It's also trigonal plane,
Yeah.
right? The third substituent is the hydrogen there on the sp2 hybridized.
Yeah,
The
and-
next one. What about the next one?
No,
2 hydrogens, right? So
Yeah.
2 of the substituents are the same, so not a chirality center. How about this one?
no. Yes. This
Yes, because
is the
look.
chirality
So
center.
draw. Why? Because you see, it has a hydrogen. Right? It has a hydrogen attached. And then what are the other substituents? You see, you have the stuff going up,
Oh, yeah.
right? Which is something different from the stuff going to the left.
Okay,
That
so
whole carbon
would
chain.
I do
and
like
then the other
this?
yes, the whole thing. And it doesn't end there. It keeps going. It's like the whole molecule. But you see,
Okay.
going up, the substituent going up is not the same as the substituent going down to the right and down to the left. Those are all different.
Okay.
If you go around those rings, they give you different stuff. So that's a chirality center, absolutely. So we'll take some of those things off.
So it's
Good.
like when you do RNS, like finding the priority, it's kind of the same idea that there's.
Yeah, exactly. So if you get different, oops, what I want to do is move your. I want to move your center a little bit. Let me see.
Ooh, okay.
So when you draw the chirality centers, I said put an asterisk, but put it below. Put it a little bit, not directly onto the atom, right? But that's a chirality center, because you could think, the other way you can think about it is you can think about about priorities, right? If going to the right, for example in this direction along the ring, gives you a different priority than going along here or going along here, then clearly it has to be a chirality center. It's not the same. And you have 4 different substituents because the hydrogen is also there. Okay, so that's a chirality center. And let's see, so then let's go on. There's more. So it's a big apple. So what else do we have?
Okay, so
This one is not,
No,
right?
yeah.
Because 2 of the methyl groups are the same.
yes.
Then
No.
same for all these guys. They're all not,
No,
right?
Yeah.
And then there's one more.
And so this would also be a chirality center.
Yes, because it also has 4 different substituents.
And could I just put that here?
Yeah, that's good.
Okay.
Questions? Yeah.
About, for the second chirality center that you pointed out with the hydrogen.
Yeah.
Do we always, when it's not drawn there, are we just assuming that it's gonna be dashed in the back?
Oh, so the question is, I'll just repeat for the recording. Question is if there is a hydrogen, if the hydrogen is implied because it's a line drawing and it's not drawn, is it always pointing to the back? Not necessarily. No. If it's so, generally what happens is it will look something like this. Let me show you. So generally what people can do, what usually in this case, I'm not giving you whether it's a dash or a wedge. So I don't want to show you where the chirality centers are. But in reality, what usually people will do is they will, for example, show that these two guys are coming, are dashed. That means that the hydrogen is then pointing back. Actually, in many instances, in a chirality center like this one, people will draw in the hydrogen specifically as a dash or a wedge, right? And then that will tell you whether it's R or S. So, for instance, it could be drawn in like this, in which case it's coming to the front. And that means the other substituents are going in the back. Or it could be drawn, to the back. And so, people will draw it in, generally in structures, to show you whether it's coming forward or backward. So depending on where the other substituents are pointing, you can infer whether it's pointing back or forward. But in this structure, like this, you cannot tell. It could be either forward or backward. Does that make sense? You couldn't tell from this structure, unless I give you wedges and dashes for certain atoms, either the hydrogen or others, right? Does that make sense? Good question. All right, those are all the chirality centers. Good. Next one, right? If you guys have no other questions, let's move on. This one. What's the relationship between those structures? Are they identical? Are they enantiomers? Are they diastereomers? Are they resonance structures? What are they? Identical. Okay, why? Because you look at this, you might think, okay, there's maybe a chirality center there, but there really isn't, right? Why? Because two of the substituents here, these two ethyl groups, are the same. Okay, so that's not a chirality center, and that means, you see, all I did going from the left structure to the right is I flipped the wedge to become a dash, right? And so we said when you do that on a carbon with a chirality center, you will get the enantiomer, right? Or if you have two chirality centers and you do it for just one, you get a diastereomer. Okay, but you get a different stereoisomer usually. But in this case, because it's not a chirality center, it just gives you the same compound just to rotate it. Okay, so these are just rotated. And how do you rotate it back? You see there is an axis here. And you pretty much just rotate around this axis by 180 degrees. And then the substituent which is pointing back, I'm trying to, let's see. So this is this V, okay? For this atom here. This is this V, right? And the oxygen would be my foot pointing back. So you flip like this, and you get to the other one. You guys see that? Literally, that's what's happening. This kind of motion we do a lot. Okay? But you have to imagine it. You could do it with a modeling kit, so you don't have to dance around. Okay? So you get the point. So the correct answer is they are identical. And maybe I'll eat an apple myself because good apples, I know. So they are identical. Okay? All right, any questions? I think my flip that showed it to everybody. What's going on? Okay, let's go on. Draw the enantiomers of the following compounds. I mean, this is just one and then the second one. You want to try this one? Okay. Here we go.
Hexagons might be a little awkward.
That's fine. That's fine, and I'll give you an apple.
Okay, this one is super ugly.
I think it's correct. Right, you flipped both stereocenters. Right, we have a stereocenter here and the stereocenter here. You flipped both of them, right? Making dashes, wedges, and wedges into dashes. That's one way to do it. Okay.
Change the location of the double bond? No, because then it's impossible.
So if you change the location of the double bond, then it's not correct anymore. So you see, you can basically, this is correct, but there's other ways. You could turn it. You could change the location of the double bond, in which case you change the way you mirror it. Basically, you have to mirror it in different directions. And I'm about to. I mean, I already wrote out this stuff. I just have to record my voice for this video where I want to show you how you can mirror a compound. You can mirror a compound in different ways, okay? So if this is the compound here, you can put a mirror plane underneath and you mirror it, right? Which is actually what you've done here, okay? If you think about putting a mirror plane like behind, or basically underneath, behind the compound, then you get this thing as the mirror image, right? But now what you can do equally well is you can put a mirror plane right here and mirror it over here, in which case then the double bond would end up on the other side, but these two stereocenters, this would still point up and this would still point down. Okay, see that? So that's equivalent. And then it's just the same enantiomer, but just drawn, like rotated. Okay, you can rotate them back. The other thing is you can mirror, so you can mirror behind the molecule, in front of the molecule, underneath or on top, whatever works. Okay, whatever you like. Good. Bonus question. That might be a hard bonus question. Can you draw a chair conformation of this thing? Try it. Yeah. If you want, I don't know. Or somebody else want to try? I'll shrink it a bit so we get some chair. Has some space. Hold on. Let me try to shrink it. I can't do anything. Let me just move it up here. How do you draw a chair conformation? We can do it together, okay? If you want. This would be a hard question. This would be like a bonus, or maybe like on the harder side. Maybe part B. So how do you do it? You want to try? Give it a try. I'll get you an apple for it. It's a hard question. I'll help you. You start off with one chair.
Okay.
Start off with one chair. And so this is a transdecaline-like structure. You guys see that? Did we talk about decalins? I think we did, right? Oh, there was a, hold on. There was a problem in the book, I think. So some of you have tried. So basically it's two chairs together. And so the way you're starting to draw it is already kind of difficult because you're drawing one chair behind the other. The easiest way to do it, okay, that's pretty good. It's a good starting point, but I'm gonna show you how to do it. So you start, So you start off with a chair. Let's say we start off with the right chair, okay, and we just draw a chair. So we're gonna start off. Huh? So we're going to start off with a chair. And let's draw the flipped one, like this one. Okay, beautiful chair. Now, the easiest way. Ooh. Okay. So now what we can do is we can draw the other chair next to it. Like this, okay? But you see what happens is now, if I want to draw this carbon here, equatorial, you see that this is basically pointing down, and in my chair, it would be pointing, it's pointing up over here. So what I'm going to do is I'm going to draw the ring flipped form. Okay, that tells me I should draw the ring flipped form. It's going to work better. So we're going to draw the ring flipped form like this. And now I can draw this thing up. And this one, hold on. No, but it's going, did I draw the same chair again?
Yeah, you did.
Oh God, that's why. Sorry, so we go like this, okay? That's it, here we go. So now the hydrogen is, no, hold on. Now the hydrogen is up. and this thing is down. And on the other side, the methyl would be, no, the methyl is down, you see?
Oh, we're drawing that one.
Oh, I'm drawing the enantiomers, sorry. Yeah, so the methyl is down, and the other thing would be up, right? But you see now those two things are pointing right away from each other, so you can't actually connect. You'd have to close up the ring somehow like this, okay? And that doesn't fit. That means we have to flip the chair. You guys see that? So let's flip the chair, which is I thought what I drew before, but it didn't work either. So let's see. Flip.
Why does not fit?
Because you see here, these two parts. You see this part is pointing straight up, this part is pointing straight down. So it's like this. They're pointing far apart from each other. And you only have like 2 more carbons to close up the ring. And you just keep, you can't reach over. It's like too far apart because they're both axial, pointing away from each other. Does that make sense? So we have to flip the chair. We flip the chair. And then when you flip it, it should fit. So we flip it. And now, okay. So now this part, the methyl is pointing down. You get an equatorial, that's where the ring attaches. And then the other, this part, right, this hydrogen, or this carbon, okay? So this is pointing equatorial now. And you see now we can draw the double bond and another chair here, kind of. And the hydrogen here is pointing up. Okay? You guys see that? Do you guys see that? Huh? I think it's the same. Let's see.
That seems way easier.
Let me see. So it depends which one you're drawing. The one you drew. Yeah, if you're drawing this one, then this is correct.
Okay.
So the one, yeah, so this one is, those are these guys here on the right. Okay? You guys see that? The one you drew, the one on the left, is a little bit easier to draw. So you see the one on the left here would look like this. Same way, right? So the one on the left you can draw like this. It's easier because here the methyl is up, the H is down, right? And then you just connect. Then the other chair starts off equatorial. Here we go, right? Okay, so that's a little bit easier to draw. The one on the right is harder. I think it would be easier to draw the second, like to somehow draw it in a different way, where you mirror it on the right. You know what I mean? So you move the double bond to the right side. Okay? So depending on what chair you're trying to draw, it gets really complicated. This one I had to think for myself. Okay, modeling it is also a good way. So let's move on. This was not even a question I was asking you guys for the problem set, but it's a hard one, and you should be able to start doing these kind of problems. Okay? Are you guys good moving on? Let's go to the next one. An enantiomer of this one. Who wants to try? Yeah. Let me get black for you here. Okay? Here we go. Here's the pen. Okay, here's the app. Basically, flip all the stereocenters. It's the easiest way. So, you want to try to draw a chair of this one? Let me shrink it for you. Try it. Okay? So you can draw the original one, okay? Let me help you. Because it's a cyclohexane. I mean, the chairs are going to be a huge, an important part of the exam. Let's see, I can't. Move it over here. I'll shrink it a little bit more. Here we go. And this is great. Do you want to try? So try to draw the original.
Okay.
Again, this is not part of the question, but I think it is helpful for us to try drawing some more chairs. So I'll zoom in a bit so you can. Can't zoom in. It doesn't react. But you just try to draw it, not too big. See if you can draw a chair of this. This is a sugar. This is I think it's glucose actually. So that's an important compound. Perfect. So hold on. Are you drawing the original?
Yes.
You're fine.
Okay.
You're fine. Sorry, I'm just. Okay, let's see. So yeah. This is good.
I think that's everything. 1, 2, 3.
That's perfect. That's perfect. Thank you. That was pretty good for on the spot. Okay, do you guys have any questions? How did you draw that chair? You basically remember you think about looking at the molecule from the front. So this guy, right? You're looking at it like this from the front. And then you label it going around clockwise, for instance, right? So you say this is oxygen is 1, 2, 3, 4, 5, 6, okay? And so now you know we're looking at it from the top like this. And that means we're going around clockwise, right? So again, this is 1, 2, 3, 4. You see we're going around clockwise like this. And then you know that the oxygen, first of all, is just in the ring, right? Then the carbon 2, this is pointing down. So this is pointing down. You see that when you draw in the hydrogen, right? And then carbon 3 is pointing up, okay? And you see that again easily when you draw in the hydrogen, etc. That's how you do it. But you need to practice. If this was, you might already be all masters of it. So in this case, it doesn't matter. But maybe not everybody is. Okay? So let's move on. Now we are going, whenever I'm asking for absolute configuration, what I mean is RS. Okay? RS. You want to try the RS thing? Good. Can you run us through a little bit, like how priorities and stuff for people who are not? First of all, you need to find the chirality center, right?
I should have made that a different color.
Good. Hold on. So you said B is the carbon there.
Yeah.
So what's higher atomic number, carbon or nitrogen?
Nitrogen.
Nitrogen. So but you had C as nitrogen. So what's higher priority there? The nitrogen must be higher priority than the carbon, right?
Yeah.
Okay. Exactly. The H is D, and
This whole thing. Is it nitrogen highest priority?
yes, nitrogen must be the highest priority, right? Remember, you look at layer number 1. So you look at first at only the atoms attached to the thing. So this chirality center, right? The nitrogen, carbon, hydrogen. Those are the things attached. So it's layer number 1. Nitrogen has the highest atomic number.
Yeah.
And so that's A. The least priority is D, right? And so that's what you can determine from layer 1. Layer 2, then, you have 2 carbons, so you have to go 1 layer further out. Okay? So you look from this carbon, you have H, carbon, HH, okay? CHH, and then over here, right, what do you have? Carbon, right, because the double bond counts twice, carbon.
And then X out the D.
Okay, so this is carbon beats carbon, hydrogen. That's why this is priority B, and then up here we have priority C. Okay? Does that make sense? Very good. And we see here is a case, what I would recommend, where does the hydrogen point? You see, you drew it just kind of like,
Yeah.
this does it point, but actually it must be a what?
It must be forward.
No, backwards.
Backwards. She drew
Back.
that.
Oh yeah, you drew it over there. Okay. Sorry, I'm being
It's okay.
like tough. But yeah,
That was
exactly.
my
It's
D.
pointing backwards.
This was my D. There you go.
That's D. Yes. So why am I saying back? Yeah, you drew it on the right side. Sorry, I didn't even see it. I was like, because I was talking. So, but yeah, it's already pointing backwards. See, that's a case like what we talked about before. Okay, where it is implied that here the hydrogen is really pointing, because you asked that question, right? Where the no, who asked it? Yeah. You asked that question before, right? Whether it's pointing backwards or forward. So here, this one is back because this so-called pyridine substituent is coming forward. So the hydrogen must be back because these other two are in the plane. Okay? Remember, whenever you have a tetrahedral carbon, you can draw it as two lines, like two substituents in the plane, and then a third one coming out as a wedge and one as a dash going into the plane. Every tetrahedron you can draw like this. So that means the hydrogen here is pointing back. Okay? And I think the rest is then clear, right? So then we have hydrogen back. Oh. Hold on. Let me see. Yeah, I think it's fine. You rotated it a bit now. So you have to always be careful not to rotate it too much, otherwise you suddenly get the other configuration. Yours is fine. But the way you drew it is the nitrogen here is kind of pointing more to the right now than it was over here. So for a while I was worried that it switched. But it didn't. It's fine. Okay? So good job. Okay? You got it right. And this is S. Okay? So you see, the thing is, these problems are, it's a lot of work involved, assigning RS. So if I give you, you look at the practice exam, I think I had like 4, 5, 6 stereocenters in one compound. Just one problem. It's like a point or two per stereocenter. Right? And then some of them can be complex. Okay? So this is still a fairly simple one. There's others like, let's see, do we have another problem like this on the next one, or that's the only one? The next one is more complex. So let's look at that. But look, you have to be like, if I'm really mean, I'll give you something like this. Look, I can give you something as a chair, for instance. Right? Like this. And then, we can be like, okay, here. Look, we go. Have a stereocenter here. Right? So now you have a stereocenter back here, a stereocenter in front. You see? Even the nitrogen in this case is actually a stereocenter, so you don't have to worry about that. But you see, because here the hydrogen is pointing down. See that? So you could do RS for this kind of stereocenter, right? So you can see, for example, I can do this in my head more or less. I can be like, okay, priority 1 is the nitrogen, or priority A. Hydrogen is D. This part back here must be C. This must be D, right? Sorry. B and then C here, okay? And so now I can look at this and I will imagine looking at it from the top here. For instance, right? Looking at it like this. I imagine looking at it like this. And then A, B, C. So it's rotating clockwise when you look at it from the top. So this must be R. You guys see that? So practice this stuff. I will try not to give you like impossible things to solve, but you have to be able to do it even for this kind of stuff. Okay?
So what about the other chirality center?
Oh, the one at the back? Yeah, good question. So here, the hydrogen is pointing backwards, right? So that would be, let's erase some of it. So I will, otherwise it's all too cluttered, okay? So I'll just leave it as R. So I'll say this is R, right? So what's the one in the back? We'll say the hydrogen here is pointing back. It has to, right? And so that's again priority D. Now, hold on, let me think. so priority A. Which one is priority A?
The one attached to the nitrogen.
Which one? So this, or this?
The one going first.
The one on top, right? Because then the second layer you get right to the nitrogen. You're absolutely right. So that's priority A. And then what about which one is priority B? Which one is priority C? This or this? First one. Why? Because in the second layer over here you get more stuff. You get like a C and an N, and the N beats. No, actually the other one you also get an N, right?
But you don't get another.
But then you don't get another C. You know what I mean? So this has, so yeah, so this one is C, priority C, and this is, B and C, okay? B and C, all right? That's it, okay? Now, hydrogen is already back, so it's A, B, C, so it's R. Okay? That's good practice. Let me just write R over here. Okay? That's how you have to be able to do it. You basically look at the stuff, you figure it out, and you can assign it within a couple minutes, even for complex structures, okay? So let's go to the next one. This one. Again, two chirality centers. Where are they? Here and here. Who wants to assign R and S? No. You want to try? But you can do maybe you can do one and you can do another one. Okay. Do we need some more male representation? So you did one of the problems. We are heavily female dominated here. So
I'm doing
but I
that
think there's
one.
More female students in that class. And I'll look at the name. All right, let's see.
Okay, wait. I'm having trouble reading my handwriting.
That's fine.
Sorry.
Okay.
Oh, yeah.
So one thing, okay, that's a note of course, that's fine. See one, but you see what you did here, right?
Yeah.
You see here you drew this like, we always have this corner, right? Whenever we draw these like zigzag drawings. Here this is pointing up, okay? Looks like a roof.
Oh, I see.
Here
It's
it looks like a V, you see? So what did we say before? It's like when I did this dance, okay? You do like this, I can't like turn upside down, my head down. But you know what I mean? It will, when you flip it like this, everything was just pointing back. You flip the dashes and wedges when you flip from the V to the other side, like we did this morning for the Fisher projection. Okay? So you have to be very careful. The best advice I can give is keep it the same orientation. Don't flip it from the V to the roof kind of thing, okay? You can, but then just you have to flip the dashes and the wedges. Okay? Let me get you a map. Okay.
Oh, wait.
So A is
Wait,
correct.
I drew it the other way. Okay, wait.
Let me see. I need to think about it myself. I don't know if it's right or wrong. I need to look at it. I need to think about these things. I can't just do it. So the oxygen is highest priority, right? Now
There we can go.
D is the hydrogen, clearly.
Yeah.
Okay. C. Yes, B is the carbon here. This carbon. Is that right? I think so, right? Yeah, because you have. Well, let's see. So let me see. So this is this. Okay. Yeah, this is carbon, carbon, hydrogen, right? On this one, the item list. On here it is carbon, hydrogen, hydrogen. So this is why this is B, right? And then this is C. And then what's the assignment? A, B, C, and the hydrogen is forward, so it's S. That's correct. Okay, good job. All right. Okay, we're already at question 7, so we're going to get through it. So then you want to do the other one? Yeah. So what I'm going to do, hold on, why don't I just undo a little bit so we don't get confused? Or I'll move this stuff. Yeah, otherwise, if it's really confusing. Okay, so I'll let you do it. And And you just do the second one. So all I'm going to say here kind of is this is S. Okay? And you can do the second one. So I only have 3 apples. Did you already have an apple?
I'm good.
Are
Thank
you
you.
good?
Yeah.
Because the Fisher projection ones which are coming are really hard. Okay, again, hydrogen is implied to come forward, you see? Like before, because the OH is back, right? And we have the tetrahedron again with two substituents in the plane, one going dashed, one dashed and one wedged. Okay?
I realized that I drew it like you said not to, like the roof instead of.
Yeah, you flipped it now.
Yes.
So you don't have to redraw it too many times. Okay, that's fine.
Okay.
So A, right, is the oxygen, right? Let's write the priorities. Let me.
I think I wrote it backwards, but.
Okay, let me see. You flipped them, I think. I don't. Let me see. You might be correct. Let's leave your drawing there, okay? It's pretty good. So let me do it. So A, I'll move your thing a little bit over. I get some space. Okay, here we go. So A is the oxygen, right? D is clearly the hydrogen. Now, which one is it? So you see here you have carbon, that's a tie, right? So you move one further out. Here you have, you have carbon and then 2 so this is the COOH is like this. It's an acid group, okay? So we are now using partially condensed notation. Okay, so you need to know that this is an acid, okay? Coming back from chapter 2, right? And so that's the acid group, the CO2H. So one carbon over, another carbon over, then we have oxygen, 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 right, on this carbon. And over here, we have oxygen, carbon, hydrogen. Okay, so which one is the higher priority? The OOO, right, the one on the right. So that means this is priority B, and this is C. Okay, and now you can redraw it if you want, but I would recommend you do it. You know, you keep, this is a V. You guys see that? This is really a V here. Okay, so you want to keep it as a V when you redraw it. So you do like this. Just leave it as a line drawing, and you can say this is C, this is B, right? And then we have here we have D, and back would be A. Okay? And now what you can do it however you want. The easiest way for me is we just do A, B, C, which is counterclockwise. So S, but you see the D is coming forward, so you have to flip it. So it's actually is R. Right? And that's what you got S. So why did you get S? Or did I get it wrong?
You forgot to flip the top when you flip the bottom. I think.
Let's see. I'm pretty sure it's R.
So if as it stands now, it's S.
It is R. Because it goes like A, the B, C, right? Which is S. But then the H is forward, so you have to flip it. So it's R. It's R. I'm pretty sure. Anybody is still agreeing that it must be S? I am almost certain. I'm like 95% certain it's R. But I get these things wrong myself. Like I've done this. I've graded everybody wrong in the class, and then because the answer key was wrong, and then it's like this stuff can be really tricky. Believe me. Okay, so this is R, and I'm going to take your drawing off. So I think you flipped 2 substituents, okay? Somewhat. I'm going to give you an apple because this was actually pretty. Are you sure you don't want it? Okay. Okay. Oh, you did apple picking. Okay. Let's move on. All right. I think. Oh, okay. So same. But this is a little bit easier. Who wants to try? We have to redraw as a wedge dash structure, label all stereocenters as RS. You want to try? You see how beautiful this is? We can now combine different things. Chairs, human projection, with RS, with naming, right? It's like math. You can bring everything together, which makes it really hard for you guys. I'm aware of that. Okay? All right. Perfect. Yeah, this is, let's see, you forgot one thing.
Oh, I did forget one thing. Yeah.
Right? Exactly. Okay, good. There are the chiral centers, right? You guys see that?
I didn't forget a CH3, it's implied.
Your thing, let me see. Oh, that's nice. All right.
CL greater than F. Yes.
If people watch the video.
Alright. CL has a higher atomic number than F. I was correct on that, right?
Say again?
Does CL have a higher atomic number than F?
Yes.
That's what I thought.
Cl is high. Chlorine is high. That's absolutely right. Let's see. So first of all, if you think this should be high. So this is a hydrogen. Yeah, that's fine. Yes, otherwise it's correct. Otherwise it's correct. All right, let me think. This is correct. Okay, S is correct for this one. Yeah. R is correct for this one. Congratulations. It's good. Yeah? Okay. Do you guys have any questions? Yes.
So when I was originally drawing the wedge dash structure,
Uh-huh.
I just drew it differently. So I drew it like this, like before I did the.
Mm-hmm.
So would that be okay? As long as I did everything correctly?
This is correct.
Okay.
Yeah. This is another way of drawing it correctly.
Okay, good.
Okay?
Perfect.
There's many ways you can correctly draw the wedge dash structures. So again, on an exam, to make my life easier and the ones of the TAs to grade, what I might do is I might actually give you part of the let's say for the line drawing or the Newman projection, I might already draw that, and you just draw in the rest, the substituents, so that everybody will naturally have to draw it the exact same way to get the answer correct. You know what I mean? Because otherwise there's many ways you can draw it, and then every time, I mean, I have to think about this for like at least 30 seconds to make sure it's really the right structure. So if everybody draws it differently, it's going to make our grading like nightmare. Okay? But if everybody draws it the same way, it's much easier for us to check. So make sure you are able to draw it on a predefined thing. Okay? In one orientation I give you. Does that make sense? But for now, for an open question like this, it's fine, regardless of how you draw it. Okay? Any other questions? Okay? So let's move on. Now, Fisher projections. I'm sure that's your favorite thing. You want to try? But we always have the same people do it. But I know, so we'll go with you. Here we go. Try. I'll go get you an apple. So try to follow. Are you going to follow along like what we did in lecture, more or less?
Yeah, that's what I was going to do.
So you draw it as this, this Stegosaurus thing, like that. Like
Yeah. So there's
like partially cyclic conformation, right?
yeah.
Good.
So there's 6 carbons in this chain. So we're going to go like 1, 2, 3, 4, 5, or sorry, 1, 2, 3, 4, 5, 6.
Good.
So the first one and the last one don't have anything on them, or they have 3 hydrogens, but so we can kind of ignore that. And I'm going to pretend that we're looking at it from this angle. So on this first, or the second carbon rather, it's going to be coming forward. Oop.
Yep.
So you can have the hydrogen there, and then coming back is the OH.
Yes.
Sorry, that's messy.
Very good.
And then the same for this one. So H, OH. Same for the fourth one. H, OH. And then the last one, it switches because now the OH is facing towards the direction we're looking. So now OH. Oops. Where's the back button? This one?
Oh, the back up here. Yes.
That?
Yes.
All right.
Good.
And then this one's H.
It's like in the supermarket when you sign. It's very good.
Yeah. And so then we're going to draw out it with like the
zigzag kind of way.
So like 1, 2, 3, 4, 5, 6. So the first one and the last one, again, 3 hydrogens, don't really matter. But so the second one here, it's pointing up, and in the other drawing, it was also pointing up, so it stays the same.
Yes.
With the hydrogen and the OH. This next one, the third carbon, is pointing down, but in the other drawing, it was pointing up, so you switch it. So now the OH is wedged, and the hydrogen is dashed. Now in this fourth carbon, it's pointing up. It was pointing up in the other one, so still H hashed OH. This last one is pointing down in the thing. It's pointing down in the bond line, but in the other one it was pointing out. So you have to switch it again. So it should be hashed OH wedged H.
Yes.
And that's what it looks like, I think.
Perfect. I think I should have you teach this next year. This is good, okay? This is perfect. Were you guys able to follow? Yes.
So if you ask this on an exam, like, and we only gave you one, would that be correct, or do you want both the zigzag and the other one?
Oh, very good question, right? If I ask you to draw a line drawing, wedge dash drawing, and I just ask you for a correct wedge dash drawing, maybe not in the lowest conformation, then you could just draw it like this one. That would be fine.
Okay.
But what I just said before, what I might do is I might do something like this. I might be like, look, if I'm really me, or, I want to be very clear, okay? I might do something like CHO, put an aldehyde or something up there, right? To label that part. And then I might just do like this. See, so we would have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I might do this. And I'm like, fill in the substituents. Okay?
Okay.
Or even, I might do like this. I might be like, look, here are these substituents. Okay? I might be like filling the substituents to get a correct line drawing into that thing in the box. Okay?
Okay.
And this is what I might give you. So in that case, you don't have a choice.
Yeah.
You know what I mean? And it's easy for us to grade. It's very clear questions. So that would probably be my preferred way to do it.
Okay.
And, then it would be... But, if I'm mean, I might do like this. I might be like, okay, look, instead of drawing it like this, maybe I will draw it like 1, 2, 3, 4, 5, 6. Be like, look, drawing the... Did you know what I mean? So I can... This will give me a way to check whether you really understand the concept. Okay? question.
How did he know that the like on the right side were gonna be dashed and the other side were gonna be the wedges?
Which ones? These
Like, how
ones?
do you know that these ones are gonna
Oh, that these ones. How do we know that these ones are? Yeah, these ones are all dashes, and these ones also are all wedges.
be? Yeah.
Right? Because we're looking at it from this side. So think about it. Sandy Werthman calls this shooting the Stegosaurus. Okay, that's what he told me. So think about it this way: you are standing over here. Okay, you aim at this is like the heart of the Stegosaurus. You aim at it and you shoot at it. Okay, and you see you look at it from this side. So the stuff which is on the right is near to you. So this means all these things on this side will end up as dashes. No, wedges. And the stuff further away are the dashes. That's how. Does that make sense? Yeah. The easiest way, rather than thinking about Stegosaurus or anything, what you want to do is just build a model. Take your modeling kit, build a model, bend it into the shape, like all of the ones in the vertical line pointing always backwards, like this, okay? And all the other ones coming forward, bend it into that shape, look at it this way, and see how it looks, okay? Use your modeling kit, and again, the good news is you can use your modeling kit on the exam. Just literally build this stuff. Look at it. It's really hard to do this stuff without a modeling kit, unless you're like a genius and can imagine this stuff in 3D really well. If you can, use your modeling kit, okay? Believe me. But practice using your modeling kit so you're fast enough. So you can't spend 2 hours doing just this problem because you have to do all the other problems as well. Okay, same for RS. Like the complex stuff I showed you before, this bicyclic molecule, you might have a hard time seeing where the substituents are pointing. If you build the model, it's much easier. You just turn it around, you know what I mean? It's not going to go wrong, the model. Other questions? You guys raise your hands.
Yeah.
You guys are good?
I did it from the other side.
It should give you the
That's
same
fine,
answer.
right? Yeah, because you can implement.
You can view it from whatever side you want. As long as you do it correctly, it will give you the same answer. Okay? So why don't we move on to the very last problem here. We literally have 3 minutes left. Just one official projection of this thing. So you're going the reverse direction now, right? Who wants to give it a shot? You want to try? Yeah. Let me just try to get the iPad to you. That might be hard, but let's see. Thank you. So just go the exact reverse, right? You start drawing it. You rotate it around in this. Oh, you want to do
What?
it? Oh, you can use the pen if you want.
Oh, sorry.
Let me see. Thank you. So, this part is correct, okay? I'll get you an apple in a second. So here's the thing. Why did you draw the bromines on opposite sides?
Because one is in the front, one's in the back. Oh.
Yeah, one is in the front, one is in the back. But now remember, when we went the other way, right, we had to convert it, the artificial projection, because it's all bent around, right? Whenever you flip, from the V to the roof, it flips it. So I'm gonna quickly, help out a bit. So what we want to do is you literally want to reverse it, okay, guys? So you reverse it. You have 1, 2, 3, 4, 5 carbons, right? 1, 2, 3, 4, 5 carbons, and you see we want to draw it like this in a kind of a partial circle, okay, like before. And so carbons 1 and 2, they have literally nothing else attached except hydrogen, so it doesn't matter, okay? Then carbon 3, you see here looks like a roof, and here it also looks like a roof, just tilted around, okay? And so that means carbon 3, you could just leave as it is, and you leave the dash and the wedges the same, okay? So we have bromine and H. And then carbon 4, you see now has flipped. Before it was kind of like a V, and now it's like a roof. That means we flip them. Okay, so now it means the bromine becomes a wedge again. Okay, And again, carbon 5, it doesn't matter. There's just hydrogens. And now you look at it from this side. Okay? You look at it from that side, and now you see this is the same as a Fisher projection. So this would be carbon 1, carbon 2, which with H and H, carbon 3. Where is the bromine pointing? Left or right? Right. Okay. Bromine, H, carbon 4, and carbon 5, doesn't matter, and here we have H. There we go. So, one other note of caution about Fisher projections. If it's fine, you did a good job. You will get it right on the exam. I'm not worried. So what you have to be really careful about is, it matters where it points right or left. Okay? If you draw the bromine on the right here, for example, on carbon 3, then it's what was it? Let's see. I can assign it in my head. It will be 1, 2, 3. Then it will be S. Okay? Then it will be S. If the bromine is on the left, on that carbon 3, then it's R. So you see, we flip the configuration, whether it's R or S, when you draw it left or right. So you have to get it all correct. We have 2 more questions. Yeah.
Sorry, so for the ring that you made,
Yeah.
everything is technically a roof.
Yes.
So we're okay.
Yes. Everything is technically a roof.
What if you put both of those bromines on the left?
On the left, then you get the enantiomer of the compound.
So it's not the same.
It's not the same. Yeah, if you draw both of them on the left, then it's on the enantiomer. If you look at it from the other way, oh yeah, if you flip carbon 1 and 5 and you move the bromines to the other side, then it's the same thing again. Then it's correct.
And for the Fishers, do we note like which is 1 and which is 5?
Which is 1 and which is 5? No, you just have to indicate it. Again, what I might do is I might give you something where 1 and 5 is not the same and draw it already there so that you can just fill in the substituents. In general, no, in general it doesn't matter. For sugars, usually the aldehyde is drawn on top. But that's just for sugars. I mean, no, you can draw it either way as long as it's correct. Okay? Okay, guys, thank you for coming. There's like 3 more apples in the front. Just feel free to take them, okay?